Hello, this is Optics Lecture 4.1, which is on refraction. And the essential question is, what happens to the transmitted light ray when it goes into the new medium? Thanks for watching. So just a reminder, remember from the last week worth of videos, when incident light comes in and hits the boundary between two different media, some of that is reflected. We've talked a lot about that light already. Some of it is transmitted into the new medium, and then some of it is absorbed by different pigments and things. We're not going to really focus on that, but in any case, this week is basically focusing on what happens to that transmitted light. So the first thing that you should remember is that the frequency of the transmitted light stays the same. That's because the frequency depends totally on the wave source, right? The number of jiggles every second the wave source is creating. So light is the same way. When light goes from one medium into another, its frequency is not changing. So when sunlight gets to our eyes through air, through glass, through water, whatever, it has the same frequency it had when it left the sun. However, what is changing is the velocity, right? Because the velocity depends on the medium. So it's speeding up and slowing down in fits and starts as it passes through those different media. Which means that the wavelength of the light is changing too. Of course, if we've got that wave equation, wavelength is equal to velocity over frequency, which hopefully you remember from your first year physics class, that says that there is a linear relationship between wavelength and velocity if the frequency stays the same. So the velocity and the wavelength change together, and the frequency stays the same. One thing I wanted to mention, and this will become clear when you look at some simulations and things later on, is that the light isn't splitting into those three different kinds of rays evenly, right? It depends on the materials, how much of each it gets. But even with two given materials, there are ways to control the amount of the light that is reflected versus transmitted. So that ratio of the reflected to the transmitted light depends on specifically the angle of incidence the light ray is coming in at, which is kind of interesting, and also the amount the velocity of the light is changing. Specifically, we get more reflected light when the incident angle is large. So that means that we are close to parallel with the surface. And that should kind of make sense to you. If you've seen reflection off a lake, right? When you look really far away, that reflection's really, really bright. If you're looking straight down at the lake, we don't get quite as much reflection. And we also see more reflection when the velocity changes a lot. So when we have materials that have a really dramatically different amount of, the speed of light is different in the materials, we tend to get more light reflected off that boundary. So there's a new variable known as index of refraction that we're going to use to learn about the speed of light in different media. This is a material property, so it's specific to the material, and we use the letter lowercase n to represent it in an equation. N is going to be the ratio of the speed of light in a vacuum, which is like nature's speed limit. You've probably seen that before. It's a lowercase c. It's been in, equals mc squared. That's the same c. So the fastest light can go anywhere compared to the speed of light in the medium that you are interested in. So the equation is just n equals c over v. In that equation, as I've mentioned, n represents the index of refraction of a material. And the range of possible n values are between 1 and 2.4. You can never have an n less than 1 because that would mean that light would be going faster than it goes in a vacuum in a material. And that's a sort of requirement for our universe, that light can never go faster than c. So the lowest possible value of n is 1.0. Air is actually 1.00024, but for our purposes, we assume that it's close enough to 1. So light pretty much goes its maximum speed when it's going through air. But as we get through solid materials, we'll have different values of n. The biggest value of naturally occurring material, n, is 2.4, which is a diamond. So light goes as slow as it possibly can go in diamond. There are no units for the value of n. That's because it's a ratio, and as you'll see, c and v both have the same unit, so they cancel out. C in this equation represents the speed of light in a vacuum. It's a material constant, so it's always, or not material constant, it's a universal constant. It's always 3.00 times 10 to the 8th, no matter when you see that variable in an equation, and the units are meters every second. And then v is just the velocity of light. It's the speed of light in the material. And the range of possible v values depends on the material that you're in. So since air is so close to 1, we assume that the speed of light, or the v in air, is also going to be basically 3.00 times 10 to the 8th. But in a diamond, light goes 1.24 times 10 to the 8th meters every second. And that's a lot slower than it is through air, like way slower, but also it's still really freaking fast. So that's kind of what you guys should take away from this. We use this equation to calculate, generally speaking, the speed of light in a material that we are given. So we'll be using that. And sometimes you use this equation in combination with that wave equation from the last slide to calculate the wavelength. So you may have heard the word refraction before. Refraction is something really interesting that happens to the transmitted light ray, and that is that when that transmitted light ray hits the boundary between the two medium, it doesn't actually go straight most of the time. It actually bends, and that's a picture of a real piece of plastic or something with a laser going through it, and you can see really clearly that the light is bending when it crosses the boundary. It goes straight while it's in the medium, right? It's straight, and then it bends right as it goes in, and then we go straight while we're in the medium. So all of that bend happens right when we cross, and then we continue going straight. So, you know, we're really used to light traveling in a straight line, and this is something really interesting and different. So we call that bend a refraction. Those are two examples, obviously, of refraction in action. So why on earth would light bend when it goes through the medium boundary? Well, this is one of those huge questions in physics that has essentially been answered, but it really requires an enormously deep level of physics and math to understand the real answer. One of the most famous physicists of all time, Richard Feynman, wrote a book called QED, and it's in that book. If you really want to get into that, feel free to get the book, but this is not something that you can just Google and find like a short conceptual answer for. So it's beyond the scope of this class, but I hope that someday you guys will feel like you can answer this question when you take more physics. But until that day, a quick analogy for you that will help us at least to make predictions about how that light bend looks, and sort of goes along with the deep level understanding, but really is more of just like a way to help us conceptualize it at the level of physics we're ready for. So assume we have two medium. I'm going to assume that we have like pavement, which is a fast medium for materials to move on, and then mud, which is much slower. So the analogy is to think about this bend as if it was a car going from one of those media into the other. So if I have a car and it's driving straight downwards on my paper, on the pavement, it's going to have a large velocity. And actually, you can see the wavelength too. If you imagine this is not just a single car, but like a stream of cars, a whole bunch of cars. So the wavelength can be represented by the spacing between those cars. So when we're moving really fast, like on the highway, there should be a lot of space in between the cars. Now, when that first car hits the mud, okay, it's going to slow down, and then it's going to proceed at a much slower velocity into the new medium. The next car is going to stay behind it. It's going to hit the mud and slow down as well. So what we essentially have is the whole beam of cars is now moving with much smaller velocity, and the spacing between them is much smaller as well. So we have a small velocity and a small wavelength. The frequency is the same number of cars every second are going to be passing into that boundary as go out the other side, because we can't like gain or lose cars. If this was light, okay, you could draw those as arrows to represent the beams of light, and that's not actually bending, right? Those light rays are going straight, same as the cars are. When they hit that medium boundary perpendicular to the boundary, or 0-degree angle of incidence right along that normal line, they go straight through as well, and that's what we see with real light. No bending. However, when that light ray or those cars hit the medium boundary at an angle, something kind of interesting happens. So you can picture on that car that I drew there, the right front tire is hitting that mud first, and it sort of slows down, right? Picture running along with a couple friends holding hands, and one of them hits a slow patch and they slow down. They kind of like spin you around. And that's what happens with the light as well. So the car hits that boundary, the front tire kind of pulls back, swings the entire car around, and changes the orientation of the entire path of those cars. So if we were drawing this with light ray, right? Light ray comes in like that. There's your normal line that you would draw whenever we're talking about light ray hitting a surface. And the refracted or transmitted light ray is going to continue at a different angle. So we have that bend happening right at the surface, and then the light ray is going to continue straight after that. So when we go from a fast medium to a slow medium, we describe that as a path bending towards the normal line, right? If this was the path that light would have taken sort of originally, if it kept going straight, then the bend is in a direction that is towards the normal line when we are slowing down. If we have the opposite situation where the light starts in the slow medium or starts in the mud, when that car hits the boundary of the fast medium, right, the left front tire is hitting first, and it speeds up. So it kind of wants to make that car turn the other direction. It's pulling the car faster forward. And so we actually spin this way and are going to be driving kind of more away from the normal line, right? If this is my light rays. So when we go from a slow medium to a fast medium, the path is bending away from normal, just like if it was a car trying to get onto pavement. And when we're going from a fast medium to a slow, we get a bend towards the normal line, just like as if you were hitting mud. So the next question is, can we quantify the amount of refraction or bending that occurs at the boundary between the two materials? Well, light takes the fastest path from one point to any other, and that's kind of a something again that you'll talk about why light would do this. It's a probability function, but kind of interesting. In any case, I really like this comic that shows why we get this bend and how you can kind of predict it, right? If you imagine that you're a lifeguard and you have a person out that you're trying to rescue, you want to get there as fast as possible. There's 3 different routes you can take, right? You're fast running on the sand, you're slow swimming in the water, you want to get there as fast as possible. You can take path A, which is the shortest path, but the problem with that is that you get to the ocean and then you're swimming and you're pretty slow, so you actually don't get to that person very quickly. You can take path B, which is like, I've got the least amount of swimming to do, but that path is so much longer that it still takes you longer to get to the person. So the path that gets you there the fastest is somewhere in between. It's a path that you kind of maximize your overall velocity by running at an angle, and then at some point you're intersecting the water and then you jump in and start swimming. And that's the fastest path from one point to another. And that's a geometrical proof that you're welcome to tackle if you want to at some point. But the resultant equation is something called Snell's law for light. And Snell's law is n1 times sine of theta 1 equals n2 times sine of theta 2. Instead of putting those things in a table, I think it's easiest to see what those variables are just based on that picture, right? So this is a picture of light refracting at the boundary between two media, and n1 is the medium that it starts in, the index of refraction for the medium it starts in, and theta 1 is the angle of incidence, right, measured from normal in that material that it starts in. And then n2 is the medium it's passing into, and theta 2 is going to be the angle of refraction measured from the normal line as well. So this is how we calculate the amount of refraction that is happening when light passes through one medium into another. Let's run through a quick sample problem. I don't know if I have any Austin Powers fans, but a shark with a freaking laser beam attached to its head is shining the laser at the glass side of its aquarium at an angle of incidence of 30 degrees above horizontal. The light passes through the glass aquarium wall into the air on the other side. Draw the laser refractions and reflections and calculate the angle that the light would leave the glass. So I gave you a couple pieces of information. I gave you this table of materials and index of refraction that you would need to use to solve the problem. So if you're interested, pause the video here, see if you guys can draw out a solution and calculate the value, and then you can proceed with the video to check your answers in the next couple slides. Okay, so the first thing I would do is draw this problem out. I've got the water inside the aquarium with an index of refraction of 1.3, glass with an index of refraction of 1.5, and air with an index of refraction of 1. I also like to just think about what those things mean. The smaller the index of refraction, the faster the light is actually going. So we've got like starting in the medium speed material into the slowest material, which is the glass, and then into the fastest material after that. So I'm going to draw my light ray, and that's at 30 degrees above horizontal roughly. And as soon as it hits that medium boundary, I'm going to put in my normal line, because I always do that when I'm drawing reflections or refractions. The first thing I would probably do is use my law of reflection to realize that some of that light is going to be bouncing off the surface, and so I'm going to draw that in. I drew it a lighter shade of red. It's still red, but there's less amplitude, right? Because we're going to have some of that amplitude split into other waves. And then I'm going to draw my transmitted light ray, and that's going to be bend towards normal line because we're going from a fast material into a slower material. And I would also, sometimes I use fingers, and I kind of pretend those fingers are like the front wheels of the car driving along, hitting that boundary. Oh, I slow down, so I've got to bend this way a little bit. You will notice that when you're bending towards normal, that doesn't mean you're going to go past the normal. You always have to go across the normal line, right? The most you could ever bend would be almost 0 degrees, but you still have to be on the other side of that normal line. So that green line I drew, you'd never have that much bending. So now we've got our second interface that we're hitting. That light ray that was transmitted into the glass is now going to go into the air. So I need to draw a new normal line at the location where that ray intersects the new medium boundary. And again, I'm going to draw another reflection. That reflection is going to hit the surface of the water, and it's going to reflect and refract, but I didn't go that far. But this would, in theory, you could keep going with that ray as well. But what I did do is draw the second refraction into the air, and this is going from a medium that is slow into a faster medium, so we're going to be bending away from the normal. Or sometimes I use my fingers and I picture this finger's hitting first, and it's going to speed up, so it kind of drags that ray up that direction. So this is my drawing of the light as it moves through that medium. So as far as calculations go, I would make a no list. My first medium has an index of refraction of 1.3, my second is 1.5, and my third is 1.0. And my theta I, my angle of incidence in the first medium, is 30 degrees. I know I'm going to be using this equation. I'll be actually using it twice, once from water into glass, and then from the glass into the air. So for that first calculation, I've got 1.3 times the sine of 30 equals 1.5 times the sine of theta 2. So this is telling me what angle is it going to be traveling through the glass. So in your calculator, you basically want to do the inverse sine of 1.3 divided by 1.5 times sine 30. So when you do that in your calculator, you end up getting theta 2 is 25.7 degrees. Which is less than the angle of incidence was. So that makes sense because it's bending towards the normal. It's going to have the smaller angle when it comes into the glass than it did when it was in the water. Now that light ray is going to continue at that same angle, and there's geometry proofs about parallel lines and being intersected, how the angle of refraction into one material will then become the angle of incidence into the next material. So for glass into air, we're going to be 1.5 times sine of 25.7 equals 1.0, which is my final material, times sine of theta 2. And so same set kind of calculations, the inverse sine of that big mess, and you end up getting theta 2 equals 40.6 degrees. Which is what we would expect. We'd expect a bigger angle because we're bending away from normal when we go from glass into air. So thumbs up if you got that. All right, we've covered a lot in this video. Let's revisit the essential question quickly, which is what happens to the transmitted ray in the new medium? Short answer, it's going to bend, but hopefully you can write in your own words which way it bends, how do we predict it, how do we calculate, all those kinds of things. Thanks for watching.